So what we're talking about today is a bunch of different interesting methods for anomaly detection. So we were talking about support vector machines last time, and so today we're talking about which is kind of clustering. Remember we had unsupervised learning, where we're basically doing clustering. We're trying to find patterns in data when we're not really given the full answer, the full labels. We're trying to find structure, same as we're doing in this natural language stuff for word track. We're trying to find embeddings, and in PCA you're trying to find structure, but you're not necessarily using it for something specific. You're saying, I'm finding structure, I'm building an embedding, a kind of a new language of how these, of what the structure of this data is. But you can use it for anything, right? When you're doing PCA or word2vec or these kinds of methods. But in clustering, we were saying, no, I want to find a group of points that are similar and kind of draw a box around them and say these ones are all in one class and these ones are all in another class, and even though I don't know what the class is, I can tell that they're similar because they're near each other. Remember we talked about k-means and dbScan and algorithms like that, where you're looking at the density and the spatial distribution of points in the feature space. And that helps to find a structure to it, right? And basically draw circles around the points that are similar. So the question then of anomaly detection is, well, what if you have a more specific problem, like kind of, which is really a subset of this, which is to say, you want to draw a box around points, but basically points that you see as normal or abnormal, right? Right. So now we're going to have a bunch of data points that have some pattern, and we can say, okay, we're going to run clustering on it, and say, let's find a structure or a pattern amongst them. But we want to, the thing we're focusing on, rather than having these boxes be really useful, what we're really interested in is weird points like this, which we could call outliers or abnormal points or noise. There's lots of different things you could call them, that they basically don't seem to fit into any of these categories. And that's the main thing that we're focusing on. So when you do that, it changes a little bit of the assumptions you might have about learning an algorithm, because you don't need to get the full distribution here. You don't need to basically draw this box perfectly around all the points, because it doesn't matter. In some sense, it doesn't even matter. Like, say we've got, you know, two different classes that we don't know what the labels are, but as we're separating them, we say these seem to be separate. We do dbScan. We say this is really one group, this is another group. But in anomaly detection, you don't even care about that, right? All you care about is, you know, normal, abnormal, right? And so that can simplify the kind of algorithms you can use. So that's basically, it's unsupervised learning most of the time, but it's a bit of a different focus. So we could be saying that what we're trying to do here is outlier detection, I suppose, instead of anomaly detection. It could be noise removal. There's lots of different ways people could describe it. I'll often say normal, because I can't really think of another word to use for it. There's so many ways to say it, but obviously when you say normal, you don't want to confuse and say, oh, I mean like Gaussian. That's not what we mean. We mean normal as opposed to abnormal. So what is, you know, the usual points, or the most standard points? I thought I'd added this. Standard, common, you know. So as with a lot of these things, we just start with language to make sure we're clear about what we're talking about. Text, bold, font, regular. There you go. Oh, okay, that's where I added it. sorry. This is really just me updating the slides for next time. So the pattern could be spatial, something you could visualize like this, or it could be a pattern over time, right? So maybe it's about how frequent some signal arrives, or at what rate it arrives, and some other signal arrives at a different rate. That could be an anomaly, right? It could be any dimension that's causing this. It could be whether the data points are expected or not, or if they're very rare, right? So highly isolated points like this that are way outside the realm, maybe that's what makes it an anomaly. It could just be conforming to a pattern that's already been seen previously, right? If it has something like this where it's expected or a prior pattern, then you know, what are we assuming about expected, right? If we're saying it's according to some certain distribution, do we know that distribution for sure? Is it something that we're imposing? It's just good to be aware of that when you're designing a system like this, right? Because if you're imposing a distribution, that can be fine because you're saying, okay, it has to be distributed as a Gaussian because we know this about the population that we're sampling. But if you think expected means something that just should be uniform over time, that's an assumption you're making, right? Is that assumption true or not? So this is something you should question if, when you're building an anomaly system, people say that's not what we expect to see. You should know why is that expectation justified? So that's just important to be aware of. So, but the outcome of this really is that anomaly detection, like clustering in general, is a bit subjective. We can't really, a lot of times, necessarily define exactly what it is in a precise way. For any of these cases, we might define precisely that, you know, noise is anything outside this distribution with this variance, or anything with this pattern, or this far away from the data. But whatever line you've set here is kind of a bit subjective to your problem, right? Whereas when we're doing supervised learning, we're labeling cats and dogs in images, people are agreeing which ones are cats and which ones are dogs, presumably. So the answer is kind of more, we're more confident that it's a real thing, right? Whereas here it can be subjective. So that just all means that sometimes we may not be sure there is really a right answer. We're just going to try to do as well as we can at the problem. So what can be used for? Anything where you're trying to find abnormal behavior, and that might be a problem, right? So security is a big problem. Someone trying to hack your system. If they're hacking into your system, it's probably causing network or system behavior that is abnormal in some way, and that probably is a sign that something bad is happening to your system. So in security, fraud detection, those kind of things, these are anomaly detection really is the main thing you're trying to do, right? Can you detect by the patterns of, you know, traffic on your network or signals or whatever, or user logins, that something is not normal, right? It could be fraud, it could be people trying to steal money, it could be something wrong with your system, obviously. So if you're building a physical system that can have dangerous faults or be leaking energy or be close to failure, when it gets closer to failure, usually it's going to start behaving differently, and maybe the usual, you know, stable pattern of some reading is going to start becoming more erratic, and, you know, you might want to see that as evidence, like, is there a fault? Is something going wrong? So whatever algorithm you have for detecting anomalies should be able to find things like this and say, you know, if I see this, what does it mean? How do I make the decision to say it's an anomaly or it's just noise? Maybe this happens regularly, right? Right, so that could be happening if you're someone, your sensors, I guess, people trying to break into some building. It could even be natural disturbances, like this could be looking at the seasonal levels of, you know, populations of some animal in over years in wildlife, or water levels in lakes, you know, and when it changes abruptly, if you can't explain this, then it'd be something you'd want to investigate, right? So all of those things are useful ideas. Some of these, right? So we try to define it a little more, like, broadly. we're really looking for things that are significantly different than some kind of normal basis that we've been given, like a regular pattern. But we want to be able to define significant, we're able to define regular, and depending on how those are defined, you get a different algorithms that work well at it, right? And so how do we define what different means and what regular or normal means, right? So we talk about it being that ideally is what we want to do, but there's different ways this is dealt with. So it could be, usually I'm categorizing this under the unsupervised learning part of the course, but as with everything, there's usually multiple flavors you can do use for this. So this could be a supervised problem, and I think on the next slide I say that again as well. Yeah, but I'll put it here just as well. So you could see this as a supervised problem where someone says, okay, I'm going to give you a data set with normal data points and outlier data points, and I'm going to label them, right? I'm going to give you something where I meticulously go through and say, here's the data points that were outliers, here's when the system failed, say, and when this failure happened, we should have detected it and done something. So they're labeled, so you can do normal supervised learning classification where one of the classes is, failure or noise or anomaly, right? And you're trying to basically get really good at predicting that class, and that's your anomaly detector. So you can treat it as a supervised learning problem if someone gives you labels that tell you which data points are noise or outliers and which ones aren't, right? So there's different ways of treating that, and there's not really a hard rule about it. Everyone seems to have, when you read about it, people have different definitions of, like, there's outlier detection, there's anomaly detection, there's noise removal is another one people talk about. And they're all really different sides of the same task. And so whether one is anomaly detection or not is not really as important as just the fact that sometimes what you're dealing with is trying to find this small set of data points that are not normal, right? So when people talk about outlier detection, they're more talking about those data points that are far away from the norm and it's well defined. And so that's just one approach. Novelty detection, the difference here means that the data points that are outliers have never been seen, right? The idea here, and I think I didn't update this from where I found it initially to add more context, is basically you don't have the outliers in your data sets. You've been only given data that is basically the normal regular data set that you want to learn. And then if you ever see something different, you're detecting a new point. So you don't know if it's an outlier or noise or just a new type of data point. So maybe you've never seen this category of object before. So you could say it's novelty detection, right? Trying to detect something new. Or it could be defined as noise because you say anything outside this distribution is noise versus normal. So they're all different sides of the same task, right? More concretely, we have to decide how we're going to treat it as an algorithmic problem, right? So if we're treating it as a supervised learning problem, as I said, you're doing something where you do have labels. You can define what it means for something to be an anomaly. You can pick one of the classes. So if you've been given, a data set with 7 classes, you can set class 1 to be anomaly, and then now you have class 2, which is actually, the union of classes 2 to 7. Then you have an anomaly detection problem where you're just trying to basically get good at detecting one class versus all the others. That's one way you can do it. The hard part that will be shared amongst all of them is that the anomalies are usually, it's an unbalanced data set. So you have a small number of classes versus all of the other data, right? Right, this is everything else. So that is a challenge for any of these algorithms, that you're trying to detect one class with lots of data that might be very complex, and the only thing that distinguishes this one is from this one kind of small class, which might be outlier or might be just one small area of the range. So we'll talk about one class SVM, which is one way to do this, which basically tries to find a line that divides the data points from normal to kind of outlier, but uses the data that's been given and essentially treats it as a two-class classification problem, where one of the classes is 95% of the data, and the other class is the outliers, and that's how you define the SVM, but otherwise it's still an SVM. And you can use any other normal classification algorithm for this as well, and just say we're going to be really good at classifying this distinction, and then it will detect an anomaly by the fact that it's class 1. A bit more interesting, and this is where we'll start, is talking about other methods that do unsupervised or semi-supervised learning, where you have a little bit of information about the data, but not that much about it, and you're using that to learn a structure that will do anomaly detection more specifically, knowing that you're looking for rare data. Okay. Yeah, and this is just saying the same thing I had. I think this is literally the Wikipedia definitions, which I wasn't going to put on a slide really, but it's another just way of rewording the same stuff that we're talking about. Supervised and unsupervised approaches. Another aspect, and this one didn't format properly. I should go back and figure out why. The only thing here is that some of these algorithms are going to be able to work online, right? Which means that they can keep accepting new data after they've been trained. And most of them will be offline, so that they take all the data at once. They learn kind of a clustering solution, a model that you can use for detecting anomalies. But then once new data arrives, you can only query it and not update the model without reprocessing everything. But some of the algorithms can deal with new data and actually update themselves as they go. They might be a little slower, but they're adaptable that way. So motivation, obviously, we want to do this so that we can solve those problems, right? We want to be able to catch the hackers, catch faults while they're happening, make sure medical scanners aren't breaking. If you're making a system that has safety issues while it's running, you don't want it to fail without knowing something's happening, so you want to detect failure before or why it's there. I don't have an answer to why we aren't done yet. Obviously something people have been looking at for a long time, but it's fundamentally hard, right? Because you don't, in the hardest version of the case, you're not given examples of anomalies, and you can't know what they are until after the fact, and it's a bit subjective. So you're never sure if you're done making a perfect model, and you always have to see more data to kind of figure out how to detect problems. So it's kind of a challenge, a thing that will never be finished, trying to learn ways to do this properly. But it's just fundamentally harder than a supervised problem. But there's a lot of standard things you can do. So stuff you guys have probably done in like signal processing classes, you could imagine. So like say your data is a time series of some sensor or some reading off your system. The simplest thing you could do here then is say we're looking for anomalies being irregularities in the data, right? That you're taking some statistic of a reading that you have, like what's the average temperature of your system, or what's the light level from your camera, and as long as it stays within some distance of, say, the median value for that over, every 5-second period, you say nothing's going wrong. If it goes outside that range, then it's an anomaly, right? And so you could set up a rolling window over these data points and computes one of these statistics or something more complex. And you could do a low-pass filter, or you could do a Kalman filter and try to basically build a probabilistic model of whether this change is likely or not, and when the change becomes significant, then you have a system that says once it goes above this threshold, or the change is higher than a threshold, then it's an anomaly. So what you're really building is a decision system that is monitoring some function to tell you whether to send a message to the user that an anomaly has been detected, right? And then the user has to decide what to do with that, right? So this is fine. It won't happen if noise or anomalies are not something that don't show up as a deviation from the statistic you've used, right? So maybe you're using the mean and this thing doesn't really show up comparing to the mean, it shows up compared to some other statistic, or it's more about a pattern across time, right? So it might not find it. It could also be that what a normal or is not static, right? So in security, you can't just come up with a predefined function that says, okay, here's what hacks look like in the system. When somebody hits your server with this many messages per hour from these kind of addresses, it's a hack. It's going to change, obviously, right? They're going to adapt to whatever you do. So you have to constantly come up with something new. So you can't just write down a function and do this. And it could be that it's seasonal, right? So that if you're looking at purchases from credit cards and you're trying to detect fraud, purchases from credit cards change with time. They've changed because of the pandemic. They change because of holidays and weekends and evenings. So your model has to incorporate all those things as well, right? So if there's seasonal effects or some kind of cyclical effect in your data and you're not accounting for it, then a simple model like this will tell you there's anomalies when there aren't any. So obviously that might have some problems. So this data set, so some of these slides are coming from a presentation we did last year from my research group. We had a paper on anomaly detection algorithm, so there might be a few slides where it sounds like we present a new algorithm, and I actually was using a slide that we presented at that conference. This is one of those, whereas the data set we were using for this paper, and it's a network data set, right? So we're looking at, it's a standard data set used in anomaly detection like research. And they took a whole bunch of network data features like the message flow, the packet arrival time, the number of packets being sent back and forth on the network, and gave them as data that you can just basically read in from a table. But they also have flags about when something happened that was considered an irregular, like an attack on the network. They purposely created these attacks and changed the data so that it's a challenging data set that people use for comparing detection of anomalies. And so this plot, I'll show this again at the end after we've talked about some of the algorithms of, what is it of? Oh, we didn't write down what it's from. It's probably the PCA projection of the data points, if I remember right, where we've got different points in the data set. We're looking at, I forget if it was like number of messages per minute or something like that. And you're trying to basically look for points that had similar properties and ones that were outliers or strange, right? So each row has a different point in that data set, and you can try to judge yourself whether there's anomalies or not, right? This bottom one seems pretty uniform. I think this is sampled from uniform data set. This might be the one we created where we just did artificial data sets. This seems more reasonable, not from the network one. Yeah, that makes more sense. So this type of data set is one way to do that, to do anomaly detection comparisons. Another way is just to create something artificial where you know that there's anomalies, what they mean, right? So this one we're just sampling from a normal, like a uniform random distribution of data points. So there aren't really any anomalies here, but every algorithm is going to try and find something, right? But then you can imagine other types, right? So two clusters of data points that are tight and a lot of noise around them, a very focused data point and another like more concentrated cloud with some noise. And so where is the division of what is normal data and what's abnormal, right? Each algorithm is going to come up with a different answer. And then really tricky ones where it's like there's definitely a clear pattern, and any human would look at this and say, okay, these are normal, these are noise, and we can decide where the edge of the galaxy is. But many algorithms that are very simple aren't very good at capturing this structure, right? Whereas a good algorithm might tell you that the points in the middle here are anomalies as well, right? So we'll come back to that, but this kind of idea of some of the types of things you want your algorithm to be able to find, right? So imagine we talked about k-means. It essentially gives you this kind of structure where you're doing clustering, right? K-means is not going to be able to distinguish these two different arms of this galaxy here very well, and it might even have trouble with this one, right?